Hey guys, this is Mr. Yo, and today what we're going to talk about is electron configuration. Now, electron configuration has a lot of information in here, but the main focus that I'm going to talk about is how to actually draw out the electron configuration. So without further ado, let us begin. Now, what in the world is electron configuration? Just by looking on the left side, it looks very gibberish. It looks a lot. But technically, electron configuration is a summary of where the electrons are around a nucleus. So, a couple things you need to know are the following notes. Now, I'm going to give you guys all these informations. I just want you guys to make sure you have the notes because I will be solving some practice problems that shows the relevance with the following words. So first thing first, we have something called electron configuration, which is a simplified orbital notations with superscripts. So to be plain and simple, electron configuration is focusing on the word exponent. That's basically what we're focusing mostly on, especially for electron configuration. Okay. The next one is called the orbital notation. It's a diagram with electrons represented in arrow signs. So the main focus about orbital notation is the arrow signs. Very important. So if I were you, I would focus mostly or mainly on these specific terms. Okay? So feel free to pause the video before you move on to the next part. Now, in an electron configuration, there are 3 different rules that you must understand. Number 1 is called the off-bow principle, or sometimes we call it filling up principle. Now, what it says is that it's the lowest potential energy arrangement of electrons in an atom. This is more of a chemistry term. Now, in an English term, for something for you guys to help understand it, is something called the chronological order. Chronological order. So basically, off-bow principle is that everything has to be in order before moving on to the next part, which I'll explain more about it as we go along. Next, the next rule is called the Pauli exclusion principle. Now, this is mostly happening in the orbital notation. Basically, what it means is that 2 electrons in one orbital with opposite spins. Basically, the arrow sign must be in 2 different directions. That's pretty much all to it. Now, if you don't know the following words, such as orbital, I'm going to call that as box. Okay? Let's just call it as a box. And electrons in this situation or scenario is going to be, the arrow signs. So these are the arrow signs that we're dealing with. Those are what the arrow sign represent, electrons. The final rule is called the Hund's rule. Equal energy orbital needs 1 electron before doubling it. I'll explain more about it, what it means, but it's just basically saying always start. So I'm going to write down always start with an up arrow sign in each box. I'm just going to say it in this format just for you guys to help understand what it means. So always start with an up arrow sign in each box. So make sure you have this information before I move on to the next section. Now, just one thing I just want to tell you, I'm not just talking about the up arrow signs, I'm just talking about the arrow sign itself. So, one arrow sign equals one electron. And I'll explain more about it as we go along. Now, before I even talk about the electron configuration and how to do it, I need you guys to make sure to have a periodic table, okay? I'm talking about those printer papered periodic tables. Not the digital ones, but the printed copies. Because if you have that copy, then it will help you understand this more. So, I'm going to draw out the periodic table. It may look a little bit weird, but please bear with me. Okay, I'm trying to be as perfect as possible, but please bear with me. Maybe I should have prepared for this beforehand. Alrighty. So here we go. First thing first in a periodic table. What I want you to sketch is the following. For the first two column and the top right corner, this section right here, first two columns and the top right corner, this is going to be called as the S sublevel. Okay. So I would like you guys to make sure for the for this information is the first and second column plus helium. That's what a S sublevel is all about. The next one is called the P sublevel. So that's located in group, or actually, let me just write it as continuation. It's 13th column through 18th column. Now, obviously, except helium, okay? Because helium is part of S sublevel. Next is our D sublevel, okay? So, the D sublevel is pretty simple because here's the reason why. The D sublevel is based on the transition metal, something that you guys have learned previously about when we talked about families. D sublevel is based on the transition metal. Okay. And then there's also one more section, which is the bottom two rows that you guys have probably seen on the periodic table. Okay. So that one, technically we're not going to go over much about it. It's just because it's a bit complicated along the way. But this whole section right here is going to be something called as the F block. Now, it's all up to you if you want to keep this or if you want to write this down. But that's all up to you. Now, one last thing before we move on to the next section is this. I would like you guys to make sure that on your periodic table that you have the column numbers or the row numbers or the periods. And when you get to the D, I would like you guys to write down the following: 3, 4, 5, and 6. There's a reason why we're writing this down, so make sure that you write down those numbers. All right, so this is the copy of the periodic table that you should have before we move on and solve problems. So, if you guys want kind of like a cheat sheet, this is a type of periodic table that you will probably be able to see on Google and help you understand how to solve some of the questions. Now, if you want more detail of it, well, here's the next periodic table. This specifies each individual elements and where they're located and how we should write it down. But I'm going to teach you guys a way that it should help you understand without even looking at these specific detailed periodic table. So, before we do anything, we want to try to solve this problem. So if I talk about nitrogen, first of all, we need to figure out how many electrons do we have in this element, okay? Or to be more specific, let's not say element. Let's say atomic number. What is the atomic number for nitrogen? Well, the atomic number for nitrogen is 7. Okay, pretty simple. Now, how about we plug in 7 arrows in the boxes? Now, remember, one of the rules says we need to make sure to plug in 2 electrons. Not 3, not 4, 2 electrons. So we're going to make sure to draw 2 arrow signs. Okay? Now, the rule called Pauli exclusion principle is basically saying the arrow signs must be up and down. What shouldn't be done is up and up or down and down. That is the incorrect way to do so. It always has to be the opposite direction. Now, if we move on to the next section, as you guys can see, the 3 boxes right here, something is wrong with it. We mentioned something before, and what is that rule called? Well, the rule was actually called the Hund's rule. Hund's rule said place 1 electron within each orbital first before placing the second electron. So in this case, since we want 7 electrons in total, we already have 1, 2, 3, and 4. So now that we have 3 electrons left over, we're going to make sure that each box contains 1 up arrow sign first before putting the down arrow sign. But in this case, we only have 3 up arrow signs, so that's the only thing we're going to draw. Okay? So make sure you guys have this correct answer down, and make sure you guys have these rules in your head so you can understand to follow those rules before making any mistakes. So now, what I want to talk about is, what is the electron configuration? So what we just talked about was the orbital notation. So this picture is all about, let me be more specific, is the orbital notation. Now, the electron configuration is that alphabet with the exponents. So I'm going to say with exponents. So how do we do that? First thing first, we're going to write down 1s. Now, how many arrow signs do we have here? We have 1, 2. So we're going to put an exponent of 2. Moving on to the next one, 2s contains 1, 2. So we're going to put 2 exponent. And next for 2p, we have 1, 2, 3 arrow signs, which means the exponent will be 3. So you need to make sure that you count the correct amount in order to write down the correct exponents. So that's why the answer is 1s2, 2s2, 2p3. If you guys are still confused, make sure you guys rewind and make sure you check the previous slides to make sure you understand each sections. Without further ado, let's go over this one. So this electron configuration is telling you basically to understand what these represent. This right here, this 4 and 4. That's the energy level. But in English, what I'm saying is the row numbers. That's basically what those are. The sublevels are the alphabets that we talked about, the S, P, D, or F. And the exponents represents the number of electrons or the number of arrow signs that we talked about previously. So make sure you guys have this down, and I'll explain more about it as we go along to the next problems. So, we talked about the Pauli exclusion principle and the Hund's rule, but we haven't actually talked about the Aufbau principle. So according to this question, does the following question follows the rule? So is this in chronological order? That's the terminology. Chronological order. Well, if you saw from the previous notes, we said 1s2, and the next thing we said was 2s2. So if you remember, S's usually come before the P's. And that is why the answer for this one is false, because 2s is supposed to be in the front of 2p. But let's actually go over some problems to help you understand it. But to do so, we need to make sure about something. In an S sublevel, we have 2 electrons. To be more specific, the arrow signs. And 1 orbital, which is the box. So let me actually show you how the boxes look. So in one box, we have 2 arrow signs. The P sublevel has 3 boxes and contains 1, 2, 3, 4, 5, 6 arrow signs. And then for the 5, if I have enough room, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you can definitely see there are some patterns going on, which is every time you have a box, you're always going to multiply by 2. So 1 times 2 gives you 2. 3 times 2 gives you 6. 5 times 2 gives you 10. And 7 times 2 gives you 14. Now for the F sublevel, I'm not going to draw the boxes because I don't have room. But also, we're not going to go over as much for F blocks, unless you're in honors or so. So I just want to make sure you guys know the basics of the basics of how to set this up. So let's try out some questions. First thing first, what I would like you guys to do is go onto your periodic table, okay? Go onto your periodic table, which I'm also going to open up one for myself. And I want you to figure out, where is oxygen? So, according to our thing, or on our periodic table, oxygen is actually located right here. In this section right here. Oops. Right here. Okay. So, how are we going to write this down? Well, here's the thing. If we know that this yellow part is the oxygen, we need to first cover the first row and the whole second row till we reach to oxygen. So here's the thing. First thing first, we start out with the beginning. What is the beginning row number? Well, that's number 1. So I'm going to make sure I write down 1. And which alphabet are we starting with? So based on your periodic table, the S started with helium and hydrogen, or hydrogen and helium. So we have 1s, and we cover 2 boxes. So each box represents an electron. So that's why we have 2. Now that we're done with the first row, let us move on to the second row. Now for the second row, what are we going to start with? Which alphabet are we starting with? Well, it's the S. And how many notes do we have? 1, 2. After that, we're still going to continue on with the second row because we are still in the second row, but with the new sublevel, which is the P sublevel. But how many do we have? How many boxes are we going to cover in total with the oxygen? Well, we have 1, 2, 3, and 4 in total. So our last step, our final destination, is to the power of 4. So make sure you guys count out, because counting is very important, especially for this topic. Okay? Now, if you guys are wondering, how do we draw this in an orbital diagram? Well, let me actually show you on the bottom part. So for the orbital diagram for oxygen, well, actually, let me make it a bit smaller. We're going to write down 1s. And remember, S contains 1 box. Then we're going to write down 2s, which contains 1 box, and 2p, which contains 3 boxes. So make sure you remember how many boxes there are for each alphabet. Now, based on the exponent, we have 2, which means I'm going to draw 2 arrow signs. We have 2 arrow signs. We have 4, which means we're going to have 1 arrow sign, 2, 3, and then the 4th one, right? Just like that. Now, some of you guys might ask, Mr. Yo, what happens if you have only 2p1? Just an example. Well, here's the thing. If you want to draw this out, we still got to draw 3 boxes. And since there's only 1, we're just going to draw 1 arrow sign. So it doesn't matter if you have less amount of arrow signs than the amount of boxes, because the boxes represents how many spaces there are. So make sure you have the spaces available, even though if you don't have enough to fill up the boxes. Let's go on to the next one, silicon. Silicon, on the other hand, if we go to Si, I'm just going to quickly erase what we have. So, oops. You guys got the concept. So, if I were to redraw this periodic table out, Si is located right at, right here. So what are we going to do? Well, we're going to go to the beginning again. So make sure you start out with what? 1s2. Because we got 1, 2. Moving on to the second row, we have 2s. We're covering the first 2 boxes in the S sublevel. Now let's move on to 2p. But here's the thing. Our silicon is in the next row, which means we're going to cover 1, 2, 3, 4, 5, 6 boxes. So 6 exponent. Now moving on to the third row, we're going to go 3s, covering the 2 boxes, which is 3s2. And then moving to the right side, remember, we still have the P block in the same row. So we're going to have 3P with 1 2 boxes covered in total. So if you're curious about how to actually make this into a orbital diagram, same process. 1s, 2s, 2p with 3 boxes and 6 arrow signs, 3s, and 3p, which has 3 boxes, but remember, even though we have 1 box with no arrow signs, it's still going to be there as a placeholder. Okay? So that's basically how you do electron configuration. So if you understand this, awesome. If you don't, well, try to keep on practicing so you can understand how to do this part. So now that you know the basics of electron configuration, but let me teach you the shortcut method. So the shortcut method is pretty simple, but you're using a noble gas. So it says, look for the noble gas, emphasis noble gas, within the previous row in the periodic table. Place a bracket around the noble gas and write the rest of the electron configuration. So for example, aluminum. We know according to the original electron configuration, we have 1s2, 2s2, 2p6, 3s2, 3p1. Okay? Now what happened if I were to quickly draw a periodic table again, just to show you guys what I meant by this part. So right now, Al, okay, is located, let's see, 13, 14, 15, 16, 17. So Al is located right here. Where is it? Here. So what we're going to do from here is that we're going to go 1 row up and go all the way to the right side to the noble gas. If you do that, you should be able to see Ne. And what's happening is this highlighted section is being replaced with the noble gas. So you don't even have to worry about the first and second row because Ne covers everything. And all you got to do now is write down the rest of the information. So that's basically what a shortcut method does. Okay? Not too heavy focused, but I just want you guys to know that there is another shortcut method that you can use to help you condense your answer. So let's try out some examples. So pause the video, make sure you have the electron configuration, and check out the answer once you're ready. Okay, so let me try out the answer right now. So we have 1s2, 2s2, 2p6, and 3s1. So remember, we go 1 row up from Na and go all the way to the right, which is neon. And this whole thing is replacing neon with 3s1. Let's try nitrogen. Nitrogen we have right now, let's see. We have 1s2, 2s2, 2p6, actually 2p3, my bad. So we're going to go 1 row up to the right. It's only technically covering just 1s2, so it's not that helpful, but it's still worth it. Just like that. Now, Mr. Yo, can we also do it for the orbital diagram as well, the shortcut method? Well, yeah. Just like what you see, you're pretty much doing the same thing. So for example, for sodium, you're going to do, first write down the bracket with Ne, write down 3s, following with the 1 box, because S has 1 orbital. And then draw 1 arrow sign based on the exponent. And that's how you do it. And that's all you're going to do for electron configuration. Okay? So make sure you guys review these notes before you move on to the next parts. and it will help you understand more to it. Now, before I move on to the next part, I want to actually go back a couple slides. Going back to the periodic table. There's a reason why for it. Okay. So based on this, one thing I want to make sure is that when you get to the D block, it's a little bit annoying. Let's say, for example, we use the periodic table to find scandium, which is located right here. Okay. So if we're looking for scandium, and I might have to erase this too. Okay. So SC, we're going to find out, well, let's do the shortcut method for now. So go one row up all the way to the right side, which should give you argon. So once you go to argon, we're going to go to the next one, which is 4s2. But when you get to the D block, this is strange, okay? The D block actually time travels one row down, which in this case, instead of 4, it becomes a 3, okay? It becomes a 3, not a 4, but a 3 with 1. I'm telling you this because a lot of people said instead of 4s2, they put 4d instead. But the reason why I put 3, 4, 5, 6 on here is because that's what the row number is when you get to that part. We'll do more practice on this later on, but just make sure that you understand this part. Okay? All right. So without any further ado, I'm going to scroll down all the way down. Oops. We're going to go on to this part. Now, this information might not be that, useful, that some people might say. But this is telling you about two different situations. A ground state and an excited state. A ground state is like an electron configuration represents where we think the electrons are at a given moment in time. Basically, it's the chronological part. So if something is in chronological order, it's pretty much a ground state. Chronological order. Then it's a ground state. So ground state is usually in the inner side, like right here. That's a ground state. And the excited state is when there are more electrons from one energy level to another. So basically electrons that aren't supposed to be there. So the excited state, on the other hand, is right here. Okay? That's where the ground state and excited states are located. Now, one thing you need to make sure is this. There are two scenarios. The first scenario is this. If the excited state wants to go down to the ground state, what's going to happen is the photon, which also means the energy, releases. Not gained, but releases. So if you lose energy, you go back to ground state. So easier way to do this. Let's say excited state is you're going to a party, okay? A friend's birthday party or so. You get all hyped up, you enjoy your time, and you run out of energy. So what's going to happen is after you run out of energy, you're going to go home and relax. That's the ground state. Okay? So after getting hyped up and you're tired, let's go back home and relax. So I'm going to say excited state is more like party. Well, grounded state is more like, being grounded or stay home. Vice versa, if we're going from, let's say, grounded state to excited state, we're going to gain photon. Okay? So if we're going from grounded to excited state, we're going to gain energy. So make sure that you understand this beforehand, because this is something you should know later on. Okay? So just know that this is information. And one last thing I just want to show you guys is this. This is called the 3D shape of each energy level, S, P, D, and F. The pictures are interesting. Okay? These are something you will definitely see in college. Okay? In college, we actually draw out these things each individually. Or maybe AP, chemistry, or sometimes honors too. But I just want to show you guys this exists and show you guys that this is not something new. This is actually something related with electron configuration. So I hope that everything makes sense. If you guys still are confused with these stuff, please make sure you go to the previous video slides or a couple minutes ago and make sure you understand these topics. Okay? Other than that, if you guys have any questions, please let me know, and hope you guys have a wonderful day today. See you guys later.